Hello! Okay, so we're getting into our last major section of this paper, which is pretty exciting. We could probably, we'll have to go back and fix up some of these, especially this last section, but that'll be eventually, and not now. But for now, we can start working on this last section. So we have a little bit of work to do here. So the core of this section is focusing on Dirichlet series, as the section is titled, and we have C n power negative s. Okay, so the definition of a Dirichlet series, kind of similar to a power series, but we have, if we have c as our coefficients, that's the thing that we're generating, and s is the variable of this generating function. So we take something c, so we'll do some little dialogue here. So I'll have to fix up this is a very short intro, but essentially we're just going to be working with this sort of function. So the thing that we're generating from is this c, and we end up with this function as a function of s. So the way that this is similar to a power series is that we can actually rewrite this as just as a for example. We could write this as, instead of n to the power of negative s, we could have e to the power of negative s, and then to the power of log n. That would be an equivalent representation. So if we had a log n going only through integers, of course this wouldn't happen. So another way we could do this is if we just did a change of variables. For example, z equals e to the power of negative s divided by log 2. That would be an example. So let's see how that goes out. So if we did a change of variables like this, then this would end up being sort of like a power series. So under this change of variables, we get, well, e to the power of negative s. This is just z to the power of, this should be the other way around. Yeah, this is z to the power of log 2. So I think this should be the other way around. This should be negative s times log 2, and then we get divided by log 2 in the change of variables. So we get something like this, or instead of doing log n divided by log 2, this would just be log base 2 of n. So if our C coefficient sequence was such that it was only non-zero on powers of 2, on indices which are powers of 2, then this log base 2 would always be an integer, and this would actually be a power series. So under a change of coordinates, a Dirichlet series is a generalization of a power series. But anyway, that's not very important. That's just sort of something interesting to keep in mind. So they're very similar to power series, just have a little bit more degrees of freedom in a certain sense. So this is our generating function. This is our Dirichlet series. So usually Dirichlet series are usually they are talked about in terms of the variable being a complex number. There's no reason why we can't do that. But we could just as well extend this to our wider space. So typically the variable s is taken as a complex number, but there is no reason why we can't consider it as a member of A, so a general member of A. So the thing that we first want to concern ourselves with is when will this series converge? When will this summation converge? For what values of C? And so we're going to have sort of a pretty weak result. So on the convergence, we only care about essentially we only care about finding a neighborhood of convergence. We don't care about putting a super tight bound on it. So we're just going to have our first theorem. So we'll say, actually we want to define a function first. Okay, so to study this function, or rather to study Dirichlet series, we need some results on where, or rather when and where it will converge for a given C. So on where and for what values of S it will converge for a given C. So we're going to define an operator to do this, similar to how we had defined our capital Phi operator to figure out when a power series will converge. We're going to define a theta operator to figure out when a Dirichlet series will converge. So we'll say given any C in A, we define the function capital theta mapping A to this will be the extended real number line minus infinity to infinity. So for any C, we have this definition. So theta of C is defined as, so similar to the root test, we'll have a lim sup, and then we have n to infinity, and instead of doing the root test, we're going to do something a little different. We'll do log base n of the absolute value of p sub n of C. So this is really similar to the root test. In fact, it's almost identical to the root test if we, instead of doing log base n, we could do log divided by log of n, and then using exponent rules, or rather, this is times 1 divided by log n, and then using exponent rules. This would be to the power of 1 over log n for logs. So these are equivalent characterizations. In fact, the term in the limit is the same. Thing. This whole log with this other one. This should be. I didn't get the. Should be like that. I didn't get the fraction. There we go. So instead of doing 1 divided by n, we're doing 1 divided by log n, and we're also taking a log. So we could also consider this as being, since log is continuous on the extended real number line from 0 to infinity, So log is a continuous, strictly increasing bijection, which maps 0 to infinity inclusive to minus infinity to infinity inclusive. We could just as well put this out outside of the limit supremum. That would be the same. And then this is actually just, as soon as this compiles, this is actually just the log of the phi value under a change of coordinates. So instead of doing n measured as just 1 over n, we're doing 1 over log n. We could also equivalently do something like, you know, e to the power of n, or we could do something like this if we did a change of coordinates for n going to the exponential of n. So this is basically just, it's essentially it's essentially the exact same brute test as the phi function, except we're taking its log once we get it. And we also have, so right here we have this really weirdness right here. Also what we're doing is we have, we just have more spaces in between, essentially. We just have more indices than the root test. So normally we do 1 over n. But we could also consider this, instead of n going to infinity, we consider this as like x going to infinity. That would make more sense. And we do floor of x. Anyway, so it's really similar to the root test, just under a change of coordinates, which is exactly what we want, because we also know that our Dirichlet series is really similar to a power series, just under a change of coordinates. But using this, we're going to have several characterizations, really similar to how you had several characterizations of our phi function. That could help us a lot. So we can actually essentially just restate, we had a theorem on our phi function. So where was that? Let's find it. Okay, so we had way up here, this. So we had these 3 following equivalent characterizations. So we essentially have exactly these characterizations, but instead of having phi power minus n, we're going to end up with n power, you know, negative phi or something like that, or n power phi or whatever. So it'll be really similar, but instead of doing these geometric exponentials, we'll do polynomial exponentials. So we can say, so this is extremely similar to a phi function, except that we have well, let me figure out how I want to say this. So this is really similar to the phi function, except under a logarithmic change of coordinates. Yeah, similar to the phi function, except under a logarithmic change of coordinates, and with extra indices. So we can also say, given this, we have the following equivalent characterizations. Using very similar proofs. So I can just essentially just copy these and just change the coordinates for all of these. So let's grab all of this and go all the way down here to where we're working. That would be here. Okay. So the theorem would be for any, we'll do C and A. following are equivalent characterizations of theta. And so we have, instead of phi's, we'll have thetas. Instead of alpha, we'll have c. Okay, so the first one is just the standard definition that we've already presented. So that would be this one. It's a lot simpler because we don't have to do the supremum. The next one would be, so we have the infimum of phi greater than 0. Instead of phi, we could do little theta. Little theta greater than 0, such that this limit, as n goes to infinity, and we'll have p sub n c instead of alpha n. Instead of phi power negative n, it'll be n power negative theta equals 0. And for this third characterization, it's also an infimum, and instead of theta greater than 0, sorry, instead of phi or theta being greater than 0, I think it's greater than minus infinity, which is just in reals, because we're doing a logarithmic change of coordinates. Such that there exists an A, and instead of A in real, we could just say there exists A greater than 0. Such that, and we could actually, to make this probably clearer, we could probably keep using alpha instead of C. Just to sort of keep with the parallels. But this is what these characterizations should look like. So, so we have this lim infimum of log base n, this. We also have the second characterization. So we take the infimum of theta such that this limit, so we have the nth projection of c times n power negative theta, this would be 0. And then this third characterization is the infimum of theta such that we can find this bounding sort of term. So yeah, I am actually, instead of using C, I'm going to use alpha. So, because that's essentially how we're using it. So coefficients alpha and variable s given as follows. Instead of starting with C, we'll do alpha. So just want to be consistent. And we'll just leave, I think we'll just leave the proof for now as not proven. The proofs are all really similar to the ones that we did for, in fact, they're much easier because in this case, we're no longer using a sequence in A, we're just using an element in A, which we're considering as a sequence in C, as a complex sequence, in that sense. So the proofs should theoretically be identical, but much easier. Anyway, this is what we have. Well, it is pretty much identical to the ones for phi. I mean, we could run through them if you'd like. There's really no reason that we cannot. It would probably be pretty fast as well. So actually, if you'd like to, just say so and we'll do it. Okay. So I'll just say, yeah, I'll just leave it like that. We could also possibly, probably what we could do, actually to make this even easier, is we could actually go up in this section for phi. So what we've done in this section for phi is we've said, so where is our definition? Right here. So we're doing this limit in terms of this variable n, which is a discrete variable. We could just as well make this a continuous variable. So instead of doing limit as n goes to infinity, we could just instead of saying alpha is a sequence with n0 as coefficients, we could say, we could just have alpha as being a function into A, which has let's say its domain as being any subset, any upper unbounded subset of the real numbers. So any subset of the real numbers that is unbounded in the positive direction. And all of these proofs would follow pretty much identically. These characterizations, they would all be exactly the same. If we did that, then that would make carrying these characterizations over to theta extremely easy. In fact, we could literally just say that because we have these characterizations for phi, so long as we do the right change of coordinates, that it's literally actually the same proof. It's extremely identical. But maybe we'll do that in the future. This idea that we can do this phi function on a continuous domain is very useful in analysis in general, and converting it over to the logarithmic coordinates to do theta is very similar. But essentially the key intuition in this theta function is that where in the phi function we were comparing the growth of our sequence to a geometric exponential, in this case we're comparing it to a polynomial. So we're saying our theta value is trying to figure out what are these values of lowercase theta that make our projections Pn alpha. What are the values of this theta that make these really similar? So we can sort of approximate the largest growth trends of our alpha by just using n power theta. Essentially, that would be right here, in fact, n power theta. That's essentially the idea. So instead of approximating in terms of geometric exponentials, we're approximating in terms of sort of polynomials. Except they're not necessarily polynomials. It's sort of polynomial-like term, because we could have, potentially theta could be a fractional value, it doesn't have to be an integer. Anyway, so for example, approximating like using square roots. But in any case, that's a good question. So I think it's better to reduce the repetition. That's generally what I try to do. But it's hard to say. I think there's an argument that sometimes repetition is good. But I think trying to reduce it down, to sort of reduce the amount of work you do, I think that's probably better. It's if the reader already understands one thing, and you can take that thing to help them understand something else, I think that's a lot better. Definitely, for sure. Yeah. But anyway, so we'll be doing, so our theorem on this is, we'll say, for alpha in A, we have d alpha s converging, and I think we'll do only if I think it's real part of P1 of S is greater than, greater than theta of alpha, let me think on this, because it should be alpha times n power negative s, which is similar to n power theta alpha. Let me just type this out real quick. So it should be n power theta alpha minus the real part of s, and this will converge when these are okay, I got it. So it'll converge only if this difference, so actually we could say alpha minus the real part of s is less than 0, and, so only if this, but it'll converge if this difference is less than -1. So this is our sort of result here that we want to do. So if we have alpha and a, then we'll have d of alpha s converging if theta alpha minus the real part of p1 of s is less than -1, but only if this difference, theta alpha minus the real part of p1 of s, is less than 0. I just had to think that one through. So the proof is not super hard. In fact, all we have to do is show that if the only if case fails, that the terms do not tend to 0. But if the if case succeeds, then we can just show that this converges using a sort of p-test. A p-test, I think that's a horizontal p-test, if you've heard of those. It's essentially just this idea. So I'll say oh, we could try something else. Let me think, actually, on that. Actually, I'm gonna get some more water, and I will think exactly how you want to state this. And while I do that, I'll be right back. I've decided what we should do. I think it's best if we do actually generalize the way that we wanted to. So we're actually going to go back right here. We're going to generalize this definition and these proofs. We're going to generalize this to any arbitrary domain, which is upper unbounded in the real numbers. Yes, and that will make a lot of things a lot easier. So for example, if we do that, then of course we'll get all of these characterizations, or at least these characterizations under the change of coordinates for free. We'll also get this result, and this result, and this result, and this result, and this result. All of these we will get essentially for free, or almost for free. We might have to redo this one, possibly, but I think the rest of these, this one will be similar, but we'll have to redo this one. But all of these other ones we'll essentially just get for free, except under a change of coordinates. So instead of doing sub-multiplicativity, I think we'll have, if we do a product, then that'll be less than or equal to the sum, because when we do a logarithmic change of coordinates, this product on the outside turns into a sum, but this will stay a product. So essentially we're just taking the log of the output. Yes, so I think almost all of these we'll just get for free, and I think we do actually need most of these in our Dirichlet series. So we're going to do just that. So we're going to generalize this function. So let's see. So we provided simple metric, blah blah. So we'll say let x be subset of real be upper unbounded. Then define, or rather, then for any alpha in a power x, define the function 5 alpha to be, let's see if that looks okay. Okay, that's fine. So the limit is x goes to infinity, and we'll do alpha sub x. And we'll actually do set alpha sub x, x is in x, and we'll do subset to a. Okay. Yeah, I think that's fine. We can also maybe modify, instead of x being subset to reals, we can say x is subset to 0 to infinity, which is, I guess, real plus. And we can just say unbounded instead of upper unbounded. Let me also, this is a typo, this should be n0. Okay, so essentially measure the asymptotic behavior of a sequence, or sorry, this shouldn't be a sequence, this should be, no, this is fine. Asymptotic behavior of a sequence where each projection is compared to an exponential. This can be defined in other common ways. So we can say, for a complex sequence, instead of saying alpha in C n0, we can say alpha sub n is in n0 subset to C. Actually, we can just say, because we don't really need to do integers. Okay, I think that's okay. Let's see how that looks. Okay, that's fine. Okay, so instead of doing n's, we'll do x's. So where alpha x is in C, then for each k greater than 1, we have pk alpha x equals 0, and the lambda supremum on x, pk alpha x 1 over x is 0. Since we have lambda supremum x p1, x 1 over x greater than 0 follows from the definition phi, supremum Okay, I think this looks good so far. So that's one proof, and we'll just have to change up. We'll just have to change up the notation. So this would be just taking x, and x by x, and reals is real positives is norm z. Okay, and then we have this. So for any alpha, instead of saying in ax, we can just do ax. Okay, so instead of n's, we'll do x's. And otherwise, I think it's pretty much the same. That's fine. I hope I'm not messing up and that this does actually hold, because this will be really annoying to undo if I made a mistake. This shouldn't be x and then 0. This should be x and x. Okay, so there is one error. Okay, so we can say, actually we need something else. So there's one way that this could break, which is that we actually need, so this third characterization will need to be changed, in fact. So we can say, for any alpha in ax, blah blah. So the problem with this third characterization is that it's possible that despite having a finite phi value, it's possible that our alpha sequence is unbounded, locally unbounded. that's going to be a problem for us. So an example of how that could happen. Good old MS Paint. So if we have, this is our x-axis, and this is our alpha axis. For example, we could have something like this with an asymptote. And then we could just continue on like this towards a constant. This would be given a phi value of, this should be given a phi value of, I believe, 0, because it does not grow or decay. It approaches a constant. If we had something like this. But this this third characterization would fail because there's no possible way to have alpha being bounded by something which is locally bounded, because alpha is, in this terrible picture, alpha is locally unbounded, somewhere locally unbounded, in particular here on this point in the x-axis. So we would have to, essentially the idea behind this third characterization though, essentially the idea here is basically just big O notation. So we can actually fix this quite easily. So we can say, instead of saying there exists an A and R such that for all x this is true, we could say there exists an A and also some x0 such that for all x greater than x0 we have this thing. That's essentially, that would be big O notation. And that's actually what we want. So we can say A in real and x0 in x such that for all x greater than x0 we have this. And I think that would fix it. I think that would fix it. And this should hopefully be fine. So all we have to do is we'll just have to account for this change in the third characterization. I think it's fine. I think this will be okay. I think what we can do is we could probably say that if the set x has no limit points, then x0 can always be taken as the minimum. Actually, we can instead of saying x0 in x, we could just say x0 in R, and then for all x in x, such that x is greater than x0. That's fine. Okay. It's a little bit more clunky, but I think that's fine. Okay, so now we'll have to double check our proof. So take any real phi, blah, blah, blah. Then we can also verify with this. For each index k, we have, instead of doing lim supremum, and we'll do x. So there is, we'll say x0 in, actually this is proving 2 from, x0 and x, after which all n greater than n have this greater than this, and thus this times phi negative n is less than this thing power x. Since phi x is greater than phi, blah blah, consequently power x goes to 0, so also this goes to 0. Okay, so we're starting from the first characterization. So there's x0 after which, and sorry, this should be x greater than x0 have this, and thus this, since phi is greater than bar phi, this is less than 1, and this goes to 0, so this goes to 0. Okay, then this should be ends again, goes to 0, proving this. Okay. And then we'll say for 2 proving 3, taking phi greater than this, so then alpha x phi power minus x goes to 0. Reaching to xk, we have alpha n phi minus n goes to 0. Let me take a look at that. Then for each index, hold on, any real phi greater than this, so then alpha x phi minus x goes to 0. Okay, naturals we have, this goes to 0, so something, hold on. Okay. Oh wait, no, this won't work either. This also won't work. Okay, I think we do have to have locally bounded. We're just going to have to specify that condition for this. That's fine. We pretty much we pretty much only want X to be a discrete set, or an everywhere isolated set. So we'll just specify that. So we'll say we could say the domain is unbounded and everywhere isolated, or we could say the domain is unbounded, and then for any locally bounded alpha sub x, okay, that's fine. Okay, so blah blah blah. Okay, so in the second condition, so we'll say taking a real phi greater than phi 2, this goes to 0 for each index k, we have this going to 0 as bounded. That's what we want to say. Since alpha sub x is locally bounded, then p sub k alpha sub x times phi power minus n is globally bounded. So select any real p sub k a greater than or equal to the supremum and this should be x, 5 prime minus x, alpha sub x. It should also be 5 prime minus x. Let me see how that looks. X minus x, okay, and thus alpha x and x, and this is preceding this. Okay. Let me double check that. So essentially we're just redoing all these proofs, but in this case where we had this general variable x. So any real theta, blah blah. For each index k, we have this greater than that, x0 after which all x greater than this have this, and this is less than that, this is less than that, so this goes to 0, and so also this tends to 0, so it's true for every k, then this goes to 0, proving this. Then for the next one, this goes to 0 for each index k, we have this going to 0, since alpha x is locally bounded, then this is globally bounded. So we can select any real pKa greater than or equal to, actually this can be a little easier. Take any real phi greater than phi 2 alpha, so then this goes to 0, we have this going to 0. And we can actually say, just immediately, locally bounded, and it is also, or rather, since alpha x phi power minus x is locally bounded and tending to 0, it is globally bounded. So we can find we can just say A is being the supremum of A of alpha sub x phi power minus x. I think that should work. And for every xk, or rather, and for every x, we get A alpha x bounded by A phi power x. Okay, that's actually a lot easier to prove it that way as well. That's nice, okay. Taking this, find this, such that this, and then for every n, you get this less than that, so that this power 1 over n bounded by, in the case, okay, so hold on. Each index this, so that, and then we do the answer to get this. In the case pKa equals 0, this goes to 0, otherwise this goes to 1, but in any case when you take the limit supreme, this is less than or equal to phi. Okay. Nice, okay, so let me just fix these indices on this third one, in this third paragraph. So we'll do alpha x, phi x, for every x. So by this phi3 condition, then for every k, we get alpha x bounded by this phi power x. And then we get pk alpha x root k alpha x root phi. This one power x goes to 0, otherwise this one whenever x goes to 1. In any case, supreme across alpha x, pk alpha x, power 1 over x, function of phi, proving this. And that's it. We're done with this part, with the characterizations. So essentially this all we need to do actually is to go down into the Dirichlet series section and prove and to prove that this I ran out of words. All we have to do is go into the Dirichlet section and then just show that phi is just equivalent to theta under a change of coordinates. And that shouldn't be too hard to do. But we'll continue on through these. So this one is pretty straightforward. So this one is exactly the same proof, just like the other one. Okay, blah blah. Power minus x convergence theory if and only if. This does, given generally this function this for any c. Okay. Okay. If a alpha x bounded by beta x for all x, then this is bounded by that. Characterization find this. It's all beta x bounded by this, then immediately it's bounded by this for all x. So that this as well, blah blah and so on. Okay. So x to infinity, x, more x's, okay, so that's this one that we just did, and then we have this one. And this one will have to be, we'll have to add some extra dialogue here. This one will still have to be, this one will have to be how it is. There's no way, we also don't need this, but there's also no way that we can port this over. I'm not sure how we would do that. It'd be really hard to do. But that's fine, I don't think we need it. Okay, so we just need to change this one and the next one. Okay, so okay. So that's here we just did. This one is, we won't be able to port this over. We're just gonna have to make a note. We're just gonna have to make a note here that, we'll just have to redo this when we get around to it. We'll just have to make a note here that for our purposes, or rather, for the purposes of power series, we will use the domain x equals n0. Domain UI snig using domain. There we go. Okay, for parsers, we'll be using domain x equals n0. Let's actually move this. We'll put this right here. And I think that's good. So that's the most that we can sort of generalize here. And the rest of this will just be how it is. So that's fine. We'll just leave this as is. So let's go back down to Dirichlet series. So now we can actually prove these characterizations. So I define the function of this such that for any, so we can say, actually let's use, so in particular, by considering the identity A equals, actually let me think about this one. Let's have alpha be, instead of being in A, which is Cn, we'll have it be in An. I'm not sure if this is really what we want to do, but it's what's happening. Variable s and coefficients alpha sub n are taken as complex numbers, but there's no reason why we cannot consider it as a more general member of A. Okay, so we're gonna have to change the theta function a little bit. So it'll actually have to be the supremum across all k and naturals of this limit, lim supremum n to infinity, 1 base n, instead of p sub n, this will be alpha sub n, and we'll have p sub k, I think. So absolute value p sub k, alpha sub n. And I think that's essentially exactly what that makes it exactly a parallel of the phi function. Let me double check. Yep, p sub k, alpha sub x, and then 1 over x. Okay. Given that log, which maps, actually we can say principal log, capital log, which maps 0 to infinity to minus infinity to infinity. Actually do ln here. Natural log, this is a strictly increasing and continuous. Projection, we have Let me pop back down right here. Okay, now we can actually do a proper thing. So we can say supremum, or rather we can say, yeah, the supremum of all of this. This would be theta of alpha is equal to this also supremum. By just doing a change of coordinates, we do this divided by log base n, or rather ln of n. And then we'll do log base n of this is ln divided by log n, which is equal to this to the power 1 over log n, and then this would say theta alpha is the ln of all of this, and then we would just have this to the power of 1 over log n. Okay, that's better. This, and then by doing, instead of doing n, we could do that, which is instead okay, I think that's fine. I'm not sure if that's 100% what we need to do. Let's bring it to the end. I think that's fine. Yeah. Okay. So we take the log of the output and we take the exponential of the input. That seems correct. Okay, yeah. So this checks out. So we're using our theta function here. So we just have this definition, and we're saying essentially we're just doing exactly the change of coordinates. And this is gonna give us, so first of all, it's gonna give us all of these characterizations for free. It's also gonna give us a whole bunch of the other rules that we had for the phi function. So okay, so this is fine. Okay, that seems fine. Okay, so we have all of these. That's fine. also have this other one that we want. Let's see. Too far. Too far. Right up around here. So we had this. We could have this. Or we could have... Okay, so we want... This one's fine. This one. I think this is the one that we want. No. Not this one. I think we want this one. Actually, we could do both of these. Oh, this is an error. This should be X. Let's fix that. Okay, so yes, okay. So we can probably maybe put these all together. So let's try to get back down here where we were. We can maybe merge all of these. Just as saying alpha, so we'll have an alpha, beta, and ABN, the following hold. So we could say alpha is this, which is this, which is this. And then we could also say in addition to that, we have beta alpha plus beta is less than or equal to the max of theta alpha and theta beta. See the end of the end? Yes, it is. Yeah. 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 We do use that. That is one of the ones. Okay. So, sub-additivity, or actually not even sub-additivity, but I don't actually know what this is called. Whatever this is. I think that's technically a hypermetric inequality, but. Okay, so then we also have, so we have this, we could try to state this, and we also want this. So we can actually say, bring alpha in A, following hold, alpha beta in A, and C in A, with C non-zero, right? Because that's this. C alpha is theta alpha, alpha plus beta is less than this. And on the last one, we have this product which is theta alpha beta is being less than or equal to, so this should be the sum phi alpha plus, sorry, not phi, theta beta, theta alpha plus theta beta. The reason it's plus is just because we've taken the log instead of yeah, so the reason we're doing sum instead of product is just because we're taking the log of the output. So the theta function takes the log of the output. And that is the only reason why we were doing sum instead of product. So let's go back down to somewhere right around, not here, up here. Okay. These are all hecka messed up. Let me fix all of these. So this, and then this, and then this. Actually, we could just name these theorems. Okay, so this is need label characterizations. This one will be phi scale independence. We'll label this one phi monotonicity. Label this one phi hypermetric, and we'll label this one phi submultiplicativity, which is a real mouthful. Oh yeah, we can also do monotonicity. think okay, that's fine. Okay, so the next thing we want is alpha being a power n, then the sum n of alpha n converges if theta of alpha is less than -1 and diverges if theta alpha is greater than 0. Actually, we can say we're just absolutely it's fine. Okay, so to do this proof, we will need, I think, I want to say both the second and third characterization. So, okay, so by, actually, yeah, both the second. Okay, so, if theta alpha is less than -1, we can find theta less than -1 having capital theta alpha less than theta. So by the third factorization, we have this shouldn't be a greater than 0. This should be the same statement, a n a re. This also shouldn't be less than. This should be like equal to. This shouldn't be Pn, this should be alpha sub n. And this should be opposite value, should be A. Okay. I think that fixed that. And this shouldn't be lim supremum log. This should be supremum of lim supremum log. But actually we don't really need to restate this. We can just cut off this. And that's a little better. Okay. Hold on, actually. No, that's fine. This is fine. Okay. Else mean and this converges if this and diverges if this. So if this is less than that, if phi theta less than that, theta alpha less than theta, which is less than -1. So by the third characterization, we have A and A sub re with, we have A of alpha n bounded by A n power minus, actually not minus, just power theta for all n, and giving absolute convergence, and that is sum n equals 1 to infinity A alpha n is bounded by the same sum. So A alpha n, we have A n power minus theta, which is just A sum n equals 1 to infinity n power minus theta. Sorry, not minus theta, I keep doing that. It's just n power theta. And this is bounded by A times okay, let me think on this. Do a sum. This should be 1 plus the integral from 1 to infinity of x power theta dx, which is just A times 1 plus, I think it's 1 over theta plus 1, if I did that right. In this case, theta is negative. Let me actually just work that out. Integrate x power t x 1 to infinity. It's negative, minus, yes, it is minus, that's what I thought. Should be 1 minus. Let's also do okay. For the other case, if theta of alpha is greater than 0, then by the second characterization of theta, we have the limit. There should be p sub n alpha. This shouldn't be p sub n, actually. This should be alpha sub n is n power minus theta equals 0. This is alpha sub n times n power, so just mean minus 0, which is alpha sub n not tending to 0. So the sum cannot possibly converge. And that's it. So that's really nice. So the thing that now we are missing is we want to show that Dirichlet series converge just like power series do, dependent only on the first projection. To do that, we're going to need a result really similar to what we did for power series. So let me verify this real quick. So this should be, instead of it should be a power n. I haven't done this most general version before. I know it works if our alpha series is all complex numbers. It's well known if it's complex numbers. But I've never done it in this general case. Which is actually kind of funny. Because technically speaking, A itself is the ring of formal Dirichlet series. And so now we're doing Dirichlet series with Dirichlet series, which is fun. It's very, very amusing. Okay, yeah, so if we have this, so what we want to say is that this will converge if this theta alpha minus this is less than minus 1, and it will converge if this is true, and it'll converge only if this is true. This is less than 0. Dirichlet inception, indeed, it's very inceptive. So this is one of the things we want to say. In order to do this, a really easy way to prove this would be to figure out what the theta value of this is. This shouldn't be p sub n anymore. This should just be alpha sub n, since we've sort of gotten more advanced. Worst case scenario, we could always just back out and just only do complex numbers. There's not really a super big reason to go inceptive like this. There really isn't, actually. Because this would be very easy if we just did complex numbers. I think what we can do, though, maybe, is essentially we want to generalize. So I'll go up. So we had way up in power series. A little further up. This result. We have 5x power n alpha sub n is equal to p1x phi alpha. This is what we had. This works for sequences of x power n. So what we know about this sequence, if we have x power n, what we know about this is that is that this is essentially, so another way to rewrite this is that we could have this as e to the power of n times the natural log of x. If x is a unit, then that would make sense. That would make sense. And so what we want to do, and then we would have n, an integer, times some log, and then the exp. And the way that we want to essentially do this is we just want to generalize this so that n becomes an arbitrary number, essentially. So how are we going to do that? So let's see. I have a little draft written up here about how we generalize this. Let's go down to where it is. This. So if we have a s in A, epsilon greater than 0, b sub epsilon, there is a b sub epsilon greater than 0 such that for all x, we have this. So this statement is a e x to the s bounded by b sub epsilon times all of this. So essentially it's really particular statement, but really what we're going to, essentially really what we want this to build up to is that we're just going to say that the theta value of n to the power of negative s is determined by, so this here, this would be, let me write this down while I think. So this is, we have a e powered x is bounded by some b sub epsilon times, we have x, let's just exp of x times the real part of s. This would be p1 of s in our modern language. p1 of s, then plus epsilon. This should be b sub epsilon. This is very similar, actually I'll do d. This is very similar to our third characterization. So we could do, this follows for all x greater than 0. We find it, pick our epsilon and s in advance, we get this b, and this holds for all x greater than 0. So what we could do is instead say, since this holds for all x greater than 0, we could say let x be the natural log of n, where n is an integer. So this would hold for all n greater than 1. But then this is just, instead of e to the power of this and so on, we would get n to the power of this, and also instead of x here, this would be the natural log of n, and then this would be n to the power of s, and then let's just change s for negative s. So we have s of value n power negative s is bounded by b sub d. So this is almost exactly the statement for theta. So b sub d times, and then here we have n to the power, and then because we have this negative s, we'll pull this out as a minus here. I think on this we have a n power negative s bounded by minus p1 s plus d. So this would be true for all d greater than 0, which I think means that the theta value is, we can also pull this d outside of the real part. The theta value is the real part of p1s, or actually we could just do, instead of doing minus s, we could just have it like this. The real part of p1 of s. That's what we're gonna end up getting. So I will keep that on the side so that I can look at it and remember it. Okay, so actually what we want, so we're going to do something similar to this. Actually we can maybe frame this in terms of the phi function. That would maybe potentially be a lot easier. Yeah, let's just do that, because I like that a lot more. So here we are, so we're way up in power series sections. Let's go back down. Okay, so our theorem will be, actually we could maybe frame this as a lemma, but whatever. So our theorem will be, for alpha, and actually we'll do for S and A, we have the phi value of the sequence e to the power of Sx indexed by x in real positives is the real part of the P1 of S, I think. Let me double check. X power plus epsilon divided by x times e power of, oh, okay, I see. It should be e to the power of the real part of S1. I think, if we're doing that. Yeah, I think that checks out. E to the power of the real part of S1. I think this is correct. So this is interesting. So, okay. I just need to make absolutely sure that I've gotten this correct. Because I feel like I'm gonna forget if I mess it up. I think this is okay. So we have bounded by the taking the power of x, and that is what the phi value is it's just bounded by the third characterization. Whatever, bounded by phi power x. Okay, yes. Okay, this is definitely correct. Okay, and this is because we get this phi value of e power s power e to the power of sx. This is going to give us. Actually, we do it a different way. We can say for s and a star. Then s to the power of x. Or let's do, actually, okay, I've got a different idea. I'm gonna change, in all of our phi things, I'm gonna change the x to an r. For complicated reasons. I know we just got through changing them all. Okay, instead of saying capital X, we'll do capital R. And instead of saying lowercase x, we'll do lowercase r. X, and replace this with R. Replace. Next. Replace. This. Not this one. Very thrilling content, I'm sure. Oh, that's sub n. This is the last one in this whole section, I believe. Okay. Next we're going to, because I also have to change, I've also changed the capital X to capital R. Okay. And this isn't even in, yeah, this isn't even in the same theorem, or the same section. Okay. I want to add, before we finish off here, I want to update this note. Okay, now that I fixed that, let's go back down here and fix it here as well. I think this is fine actually. The only place that we're using this different convention is right here. Okay, so for s and a star, phi s power r. Instead of doing e to the real power of p1 of s, so we're replacing s with, let's say, log of s. Real p1, which is unambiguous. Yeah, wow. All the stuff that we did actually worked off, actually paid off with we had all sorts of complicated things. Okay, so this is, I think this is correct. So for any s and a star, we have phi of s power r, where x is in real positives, sorry, this should be r in real positives, is this. P1 a real part of log of s. Okay, so let's see. So we'll say find any, or rather, let log of s, yeah, satisfy any element satisfying exp log s equals s, which does exist since s is in a star. Actually, we can say actually, yeah, this is fine. Okay, so let me double check. So let's see how this theorem does it. That's this lemma. Okay, so we use a decomposition here. Let's do, actually, let's say this, let Z be satisfying Z equals S, which must exist. Exist since S is an A star. Okay, so now we'll say we use the unique decomposition. We might not need to do this decomposition in the end, but we'll do it for now, because that's how I did it in my draft. Let me... That's better. Okay. So where are we? Let me close that. Right. Okay, so we'll say let Z satisfy A, so Z equals S. We'll use this decomposition, unique decomposition. Z equals, we'll do A plus BI plus whatever the remainder is, Z0, where A is the real part of B1 of Z, and B is the imaginary part of P1 of Z, and Z0 is Z minus P1 of Z. So Z equals A plus BI plus Z0. Okay. So let's see, what did we do next? So next we did... How fascinating. Okay. So we turn it into an integer sequence. Okay. So follows then that if we can have A of, we have S to the power of R is A of, we have, instead of S to the power of R, this should be EXP. Okay, let's do it this way. We'll say let Z in A be the element. Oh wait, actually maybe, what do we do here? So we're gonna run into an issue maybe, because we're being ambiguous about the logarithm in this branch here. Let's just not do this. We'll just do it the other way. Instead of doing S, we'll just do e to the S, e to the SR. This is fine. Okay, use the we use the unique decomposition Z equals A plus BI plus Z0. And instead of Z0, we'll do S0. Since we're doing this variable scheme now. Pause then that, so we have E power SR is A of E power, so instead of SR we have, instead of doing, this is fine, E power AR E power I BIR, and then, or rather, IBR, and then E power right, because A is linear. That's fine. And then this is E power of S0R. Okay. This is preceding or equal to A. Actually, yeah. A is linear. E to the A, linear with complex coefficients, or complex numbers. E to the AR times A to E S0R. Okay, that's fine. The rest of it is just bounding this A, EX as 0. Actually, this R, let me think on that. Yeah, AX S0, okay. AX S0, 0 as being equal to X A S0. Is this gonna work? Yes, it does. Okay. So the way that we handle having this discrete, I used X again, I should be using R. Okay, so the way that we're handling having a continuous variable R is essentially we're just using the ceiling function. And from here, we use the Taylor series representation. So we have A of E to the power of SR, actually it should be S0R. So this is this E, A, absolute value of this sum, n equals 0 to infinity. And the coefficients are 1 over n factorial, and then S0R power n. And this should be the sum, again, n equals 0 to infinity. Then we have factorial on the bottom. We have A of S0R to the n. And this is just exp of A. Actually, hold on. Let's fix that. Okay, this will be A0R. We'll have this. And this is just exp of this. I don't know if this will fit on online. It will. Oh, this is messed up. What the heck has happened there? Oh, that's what happened. Okay, so we've made this. That's nice. Okay. We can also have, this could be E instead of exp. Let's do that. And we'll do some little brackets here. Very nice. Okay, this is exciting. Okay. So in combination, we therefore have A of E to the SR. This is bounded by E to the AR times E to the, actually we can just do AR plus A S0 ceiling of R. That's maybe not what we need. I can maybe simplify this. Because instead of doing S, we could just do, we don't even need to do the C composition. We could just do ASR, AS0R bounded by AS0, or AS ceiling of R. And then again, instead of S0, we just have ASR, S0. Oh, wait. Nope, we do need to separate these. I remember why. Because it's important whether or not the first index is positive or negative. Instead of doing AS0 ceiling of R, we could do e to the power of something like this. Oh yeah, okay, I got it. So on and so forth. Okay, and then this would just be just like this. That's why we need the ceiling, because now this is an integer. This. Okay, and then this is essentially the conclusion. So since we have phi of e to the AR across R in R greater than 0, or rather, since e to the R is greater than 0, or sorry, not e to the R, e to the A is greater than 0, then this phi of e to the AR, what is e to the AR? We could do e to the A, and then to the R. So e to the A and then to the R. And this should be e to the A. This is real, so this is e to the A. And since the ceiling of R is in naturals, we also have phi of this we have, let me fix this, there should be just like that. There's this, we also have phi e AS0 saying R in terms of R in R positive. Oh gosh. This is, okay. This is definitely gonna look really gross. Actually, it's not that bad. Okay. Real, then phi of this should be this, and this should be, that's fine, but we've messed up this somehow. Okay. So this is exactly the same, but instead of being R in real positive, we just have N in naturals. Instead of doing the ceiling of R, we just do power N. And we know that this is just the absolute value of P1 of E to the power of A S0. And then just by pulling this through, this is the absolute value of, actually this is fine, this is just e to the power of p sub 1 of a s0, which is 0. Wow. Okay, and then I think that's it. So by submultiplicativity of phi, it follows, actually by monotonicity and submultiplicativity of phi, it follows that. phi this e to the s r indexed by r and real positive is less than or equal to, actually, is what we get. That's all we need. Okay. Less than or equal to e to the a. That doesn't seem right. Oh, that's e to the 0 is 1. I'm a silly goose. Okay. I think that's good. Let me see if we can change this a little bit. Okay, yes, we can. Instead of doing P1 on the real part, let's do real part P1. Yeah, so we'll go back over this. I think. What was some analysis thing? Oh yeah, no, not 0. Definitely not. No. E to the power of it's never 0. It's never. No. That would be oh gosh. No, I just made a mistake. A P1 of S0 is 0. And then e to the 0 is 0. Or sorry, e to the 0 is 1, not 0. Yeah. Yeah, definitely not that. That is definitely not true. Okay, so, I think this is good. So we can maybe avoid doing this decomposition if we want. But this is fine. Using the ceiling function, we have this, so that this combination, we therefore have this. Since e to the a greater than 0 is real, then this is that. So we just have this real geometric series, or real exponential series. We're taking the phi value of this exponential series. So this is just e to the a, and then since norm r is natural, a natural number, then we can just replace the ceiling of r with just natural integers, n. Because it doesn't matter. Yeah. This is maybe, this part in particular is maybe a little bit hand wavy. It's not as trivial as it looks. It's true, but it's not quite as trivial as it looks. I'm just going to ignore that though and pretend like it's fine, because it is. But in any case, that's that. Yes, okay, so then let me adjust this. So this shouldn't be equal, or at least I think it shouldn't be equal. No, wait, it should be equal. Because if we have, I think if we just take the first index, if we just take the first index, P1 of E, to the SR, then we get e to the power of P1 of S times R, and that does have this. And I think that proves equality. Okay. Okay, so we're using this decomposition, blah, blah. Okay, so this is fine. Where e to the a this is the real part of P1 of S. Okay. So P1, e to the power of SR, because e is a complex analytic function, it's just e to the power of P1 of SR. And then we can say phi of, I don't want to type this out, phi of this whole mess is bounded by, just less than or equal to, bounded by phi e to the P1 of e to the SR, which is equal to the entire same mess, but with P1 on the inside, and this one is just because it's a yeah, this one is just e to the power of P1 of S, or sorry, the absolute value of e to the power of P1 of S, which is e to the real part, because it's a complex number, P1 of S. Sorry, this should be greater than or equal to, because it's phi is the supremum of phi on the projections. So we're taking this projection, so that this has to be less than or equal to the overall phi value. And that's it. Nice, this is pretty good. This is very nice. So that this does mean actually that we can prove our thing as we wanted. So our corollary is that alpha be in a to the n, then theta of the sequence of alpha sub n times n to the power of minus s. This is equal to theta of alpha times sorry, plus, or rather minus, the real part of P1 of S. Okay. Okay, so firstly, we notice that the theta value of the sequence for n to the power minus s, n is in naturals, is less than or equal to this should be this should just be P1 of, or sorry, the real part of P1 of S. So this follows since n to the power of minus s is just e to the power of minus s log, sorry, this should be negative, log n, natural log n. Actually, we can just do a capital log n. I'll update that later. Okay, so this is this follows since this is this, so and okay, yeah, and then theta of this whole sequence where we use this expression and instead of n, actually no, this is fine. This is less than or equal to oh, sorry, okay. We have to do the theta to phi conversion first. So this is theta of, okay, so what we had was oh, that's interesting. We're just doing some math. If you like math, you can hang out. Actually, you know what I should do? So this document that we're working on should be freely available to download and read. I'm going to grab an invite link. 1 second. If you're interested in downloading or taking a peek at this file, if you'd like, you can join our Discord, and we have in the stream documents file we have this file is free to download, and you can read it as we work on it if you're interested. Let me put that in the description maybe. Okay, if you like. Okay, so where were we? So we've just gotten through this. So what we want to do is, right, so we're going to do, so we'll try to prove, so first we want this. So we have to do the theta to phi conversion. So right over here, there should be n power negative s theta n power negative s. This is, so we'll do the theta to phi conversion right away. So this is the natural log of the phi. Actually, we can do this. We'll do natural log of phi, and we just do n goes to e to the power of n. And this will be less than or equal to the same phi value, but using all real numbers. This will be the log. Oh yeah, this should be log, shouldn't it? Or should it? Let me double check that. Theta alpha is the log of phi alpha sub e to the n. And we have theta this is log phi e to the n minus s. Okay, minus s. And log of phi, which is less than or equal to log of phi of this, which is log, okay, this is fine, because we do have e to the power of the real part of p1, which is, okay, so then this just ends up being the real part of p1 of s. And then for the other direction, we should have, actually I think this is, no, this is, yeah, okay. We can try this, maybe. I wonder if this would work. Oh, sorry, this should be negative. Okay. So this is this. I think this is fine. That follows by sub follows then that phi of this whole thing. I'm just going to copy this. So phi of this is less than or equal to, oh sorry, theta of alpha sub n plus theta of this thing. Actually, we can just go right ahead with minus the real part. P1 of s and then we can also do if we just multiply back by n power s, we have theta of It should be theta alpha is, did I not do the thing? Yep, okay. Okay, that's better. This will be less than or equal to this whole thing plus the real part of P1 of S then this implies that we have this is less than or equal to that, which is less than or equal to this thing plus this thing minus real part of P1 S, and these cancel out. And we're done. We could maybe just do this in the positive sense. Instead of doing this negation. I mean, that's what we're going to end up using it for. But there's no reason to do that. Okay, so I'm just going to combine these. Theta alpha. So this is equal to this thing plus this. This thing, or equal to this thing plus that again. And so I'll just do plus with a minus s in here. And then this is equal to this. That is way too long. So we'll put that in an alignment environment. And we'll split it up into a couple lines. Put a marker there. I think I'll split it up right there. I may mess that up a little bit. That's better. Perfect. And that's it. So let alpha be any coefficient sequence and S and A, then this theta of that is theta alpha plus real part of P1 of S. Awesome, that's great. Okay, and I think that's everything. And maybe we could maybe move this if we wanted to. I think this is fine. Okay, so I think, what do we want to do here? So this, okay. So there's this, and we can actually do another corollary for any alpha and A n B, or rather, and S and A. Dirichlet series D alpha S converges if the real part of P1 of S is less than theta alpha minus 1 and diverges if real part P1 of S is greater than, that's not correct. Should be converges if this real part of S is greater than 1 minus, I think, theta alpha. No, it's 1 plus theta alpha. Yes, because it'll be theta alpha minus real part P1 of S is being less than minus 1. Yeah. It diverges if it's less than theta alpha. Okay. Since we have, or rather we can say, letting beta sub n equal alpha sub n power minus s, we have d alpha s is equal to the sum n beta n, and since theta beta is theta alpha minus the real part P1 of S, the result follows. That's fine. Okay. Okay. So that's exciting. Yeah. So I have not proven these ones previously until just now. Specifically for the general case where we have coefficients in an. The case where we're in Cn is kind of straightforward, and that's very known. But of course, in this context, I mean, I'm not really aware of very many people who actually, or any results really that works in this context other than our own. So, well, this is cool. So we have this convergence, and actually, we could maybe even go so far as to notice that in this range here, actually, it's differentiable. The function is in fact differentiable, not in terms of alpha, but in terms of s. And the way that we would do that is by showing compact convergence. So alpha n a n, the function d alpha s fixed alpha is differentiable. Okay, no problem. We've been going for actually 3 hours, so we could probably stop. I will type out this theorem and then we'll get back to it next time. The proof, I mean. The function differentiable in terms of s over the domain real part p1 of s strictly greater than theta alpha plus 1. Okay, we'll get back to this next time. Thank you very much for watching. I hope you had some fun. Whenever you have your questions, you could ask them now if you'd like, if you have time. Otherwise, feel free to just message me on Discord or whatever, because I'll always be around. Okay, bye. Good luck at algebra practice, and I'll see you next time.